Let's get started for today. Quick announcement, I'm sure you all know this, but just to make sure nobody sleeps through the midterm next Monday. It will be next Monday. It'll be right here in class. It's closed book, but as I mentioned last time, you can bring a one-page set of notes of anything you like. Yes?
It's 12 right now. Are we starting at 11 a.m.? Last bullet point?
Oh, I'm sorry. This is important. Noon. Thank you. I guess I made this one up too early in the morning. Thank you. We will start at noon. And it'll cover all the material. And people have asked me, oh, but what'll be on the midterm? Just the normal stuff. That is, we're going to cover all the things that we think were most important and that were most basic. And we're not actually trying to make up really tricky, weird questions about the 5-minute discussion that we had on Tuesday, April 4th. You know, we're not going to do that. We're interested in testing whether you know the basics of the course. So, a good way to study, by the way, is just to get together with some of your colleagues in the course and ask each other questions that you think might be the kinds of questions that we would ask if we were going to test whether you understood the material. Okay? Thank you for this correction. So today I want to continue on Bayes nets and get to a very interesting new learning algorithm. But just to kind of remind you, Bayes network, as we've said several times, is simply a graphical notation for representing joint probability distributions and how to factor them into the product of a set of terms, one for each random variable, and factors this way. So we've said that many times. What you should know most importantly about Bayes nets is this. How you actually represent them, how they do define the joint distribution. Note that you can calculate everything else from that because, as we said in lecture 2 of the course, if you actually have the joint distribution over a set of variables, you can calculate the probability, conditional probability of any subset of them given any other subset, or just the flat out marginal probability of any one or any set of them. So since Bayes nets are simply a representation of the joint distribution, that statement holds as much for Bayes nets as it held for the case in lecture 2 where we were just talking about having a table. You know, remember we had poor people and people who worked a lot of hours and male and female people, and then we had just that big table. You should know how to read off conditional probabilities. I'm sorry, not conditional probabilities, but conditional independencies that are implied by that graph. Okay, so today I want to talk a little bit about inference, but then mostly about using inference to do a very interesting kind of learning that we haven't yet discussed. In general, when I talk about inference in Bayes nets, what I mean is, given a Bayes net and an arbitrary question of the form, well, what's the probability of this subset of variables taking on these values, given this subset of variables has that set of values? Then the inference problem is to answer arbitrary questions of that form. And it turns out that in general, this is an NP-complete problem, meaning that the cost of actually calculating that, of course you can always calculate it because the Bayes net does represent a joint distribution over the random variables. So the answer is there. But the cost can be exponential in the number of variables. One way to see that is, remember our default method for calculating any probability term is just to look at the table of the joint distribution. And of course, there can be an exponential number of rows in that table, exponential in the number of variables. Right? In even the simple case we talked about in lecture 2, we had those 3 variables, male, female, hardworking, not hard, work many hours and work few hours, wealthy and not wealthy. And with those 3 Boolean variables, we had 8 rows in our joint distribution corresponding to the 8 joint assignments. So even with Boolean variables, we'll have 2 to the n rows, exponential in n, for just n Boolean variables. And so if we have to resort to that general method of counting up the rows in the joint distribution, then you could see that that would end up being exponential. But in some cases, some of those questions are tractable depending on the question you ask and the form of the BayesNet graph. We'll take a couple looks at this today. Because of that, it turns out another kind of general technique, there are really 2 general fallback techniques for doing inference in Bayes nets. One is to figure out the joint distribution table from the Bayes net and then count up the rows you need. The other is to use Monte Carlo methods, where we actually just generate samples of the joint distribution. Put another way, we generate fake data that we generate from the Bayes net in a distribution that fake data that is drawn from that joint distribution. And we'll talk about that in a minute. But those are kind of the 2 fallback general ways of doing inference. And then there are a lot of more specialized techniques for particular Bayes net graph structures that you might have. There's also a set of methods which we won't talk about in this course called variational methods, which allow you to tractably compute approximate solutions to some of these inference problems. And so if you're interested in this sort of thing, you might want to take the graphical models course that's offered in the machine learning department as a follow-up. Once you finish this course, you have the prerequisites to take that course. So if you're interested, you can take an entire semester on Bayes nets. Okay, so let's just look at a couple inference questions just to make sure we're all on the same page. Here's Bayes net similar to the one that we talked about last time. It says if you have the flu, 5 random variables here, and that having a sinus problem could depend on whether you have the flu or an allergy, and having a headache or a runny nose could depend on whether you have a sinus problem. Okay, so if we have that problem, and you should know the answer to this immediately, if I just want to know, given that Bayes net, what's the probability of this particular joint distribution? And here I'm using little letters to represent the values of the random variables, which are represented by big letters. So how would I calculate the probability of those 5 variables taking on these 5 little variable values? You should know this. Right, I just look up, I use the factorization that I get, right? So I look at the probability that the f will take on the value little f, and that's right there in the conditional probability table associated with this random variable. There's conditional probability distribution there. I just read that off. And then similarly for allergy, and then similarly for, what's the third one? Right, it's S given F and A, right? Because that's the factorization implied by this Bayes net. And then finally, the probability that headache will have this value given whatever the value S is, and the probability that I'll have N given S. Okay? That's a P. Okay, so that's just what we talked about last time. you can calculate easily the joint probability, or the probability for any joint assignment. Okay, now what if I want to know a different kind of answer to a different kind of questions, like the probability that n that knows will have the value n. Then how would I calculate that? Sorry?
Sum the marginal possibility that it has through an energy.
Right, so I could sum over all the possible assignments for these 5 variables, but only sum over the ones where nose takes on the value little n. So that's the same as going back to the joint distribution table and summing up the rows that happen to have uppercase n equals little n. So that would actually be a reasonable way to do this. I'd say the probability that n takes on little n is just the sum over, let's say, little f, little a, little h, little s of the probability that n equals little n, and I'll just abbreviate our usual way. Like that. Okay, so I have to sum over all the possible values for f, a, h, and s, but I wouldn't have to sum over the different n's because I'm only interested in the cases in the joint distribution where I get this assignment. And so here you can see this is going to be, if I have n variables, then I'm summing over n minus 1 of those in all possible values. So but when I say sum over that, what I mean is sum over f, the values that f can take on, and the values that a can take on, and so forth, right? So if these are Boolean variables, I'll have 16 possible assignments there. In general, it's going to be n minus 1 of these I'm going to have to sample over, so I'll have 2 to the n minus 1 of these terms in my sum. Yes?
But if we know if we know about sinus's distribution, we don't have to go back to flu analogy. We can stop at sinus.
Ah, very good point. So this graph tells us that nose is conditionally independent of sinus, or sorry, conditionally independent of flu and allergy given sinus, its immediate parent. So why can't we use that somehow to do something more tractable than this, more efficient than this? Thoughts? The problem is we don't know the probability that sinus equals 1 and 0. And we can't simply sum over sinus being a 1 and 0 as though they were equally probable. Right? So this is a joint distribution over 5 random variables. And it could be that in that joint distribution, if we sum up all the rows where sinus equals 1, we see that's 0.7 probable. And it's only 0.3 probable that sinus equals 0. And without knowing what that probability is, we can't simply use the conditional distribution here, which tells us how n depends on s. We've got to know the probability of s. And that's not sitting around in any of these conditional probability tables that we have. So that's the reason, in fact, we do have to sum over all the joint distributions. Yes?
But headache is everywhere. I mean, nose is conditionally independent with headache given sinus, so we can forget about headache and just
Nose is conditionally independent of headache given sinus. But again, we don't know sinus.
That's the reason we are taking flu and allergy.
Now, it really,
Some overflow and allocate to get the sinus possibly. Just like a subtree.
right, there could be things that we could calculate from this thing, but we can't use, unless these things are marginally independent, we can't really use the fact that they're conditionally independent because we don't know the value, we haven't, what it means to get this probability is that we're not observing anything else. And so we have to take the expected value of that assignment over the entire joint distribution in general. We can use conditional independence if we know the value of one of the variables. But if we don't, then we're talking about marginal independence. Okay. All right, this is another a kind of important thing to realize is the arrows, if you're upstream of an arrow, it doesn't mean, or if you're downstream from an arrow, it doesn't mean that we can ignore you. It just means this is the way we factored the joint distribution. Right. Okay, so this is really the reasonable way to get the probability of n. Okay, so let's move on to, I mentioned that so one way in general to figure out any probability term is to basically sum over the right rows in the joint distribution. And I mentioned that another way, which gives us approximate answers, but sometimes much quicker, is to actually generate fake data that follows the joint distribution and then just basically get maximum likelihood estimates out of that fake data. So for example, so how would we generate fake data? That is, how can we generate a random sample of data that's drawn according to a joint distribution given the Bayes net? And here's the hint. If we want to just sample a single variable like flu, and we want to know, we want to generate data, and say we have a distribution, it's just a Boolean variable f, and we know that the probability that f equals 1 is theta, then here's a simple way to do that. Most computer languages like Fortran and Octave and Java have a random number generator that lets you ask for a randomly distributed variable in the interval between 0 and 1. And so you can call the computer program primitive to get a random variable between 0 and 1. And then, actually let's draw it. It's like here's 0, here's 1. And so I could ask that primitive to give me a random number r, which with uniform probability will be anything between 0 and 1. And then let's suppose, for example, that theta is 0.7. Then what I'm going to do is if I draw an r and it happens to be less than theta, then I'm going to say, oh yeah, f is 1. I'm going to generate a f is 1. But if I get an r which is above theta, then I'm going to generate a f equals 0 data point. And so you can see that if I do that over and over, 70% of the time, I'll get a random number r that falls into this region. And 30% of the time, I'll get a random number that falls into that region. And so every time I draw a sample of r in this uniform distribution, I can turn it into a sample of f, which is either 0 or 1. Right? So it's just a simple trick for turning the primitive that's usually available in most programming languages, which is a random number with a uniform distribution, into a way of generating random numbers according to this distribution. Right? And if theta is 0.01, probability that f equals 1 is 0.01, then hardly any of the data points I generate, if I just keep repeatedly sampling r's like this, hardly any of them will be f equals 1. Most of them will be f equals 0. Okay? So this is a very useful technique to be. So here I'm going to output f equals 1. Here I'm going to output f equals 0. And I can generate a lot of samples very quickly this way. Yes?
If you allow me, I'd like to show that P of n equal to n does not require sufficient over infinity.
That's great. I would love to see it if we have room at the end of class, but I have things, and I'm happy to stand corrected on that. And if we don't get a chance to do it here, we should publish your note. But I just don't want to take the time in this lecture to do that. But thank you. Okay, so you get the idea. This is just a way of, for a single random variable, say a Boolean variable, to turn a uniform random number, which we can just get out of their program, into a way of generating random values of f that follow its probability distribution. And similarly, if we had a Gaussian distribution instead, we can do, it's a slightly trickier picture to show, but basically we have to show, we would use a cumulative distribution function and sample our r and index into that to decide on the Gaussian value. Okay? So this is a useful technique, and we can easily turn it, along with the Bayes net, into a way of generating joint samples from the joint probability distribution. By the way, is it clear what I mean when I say a sample from the joint distribution or a sample from the single distribution? I just mean I want a bunch of random numbers that obey whatever the distribution is. So in this case, if I generate 100 points like this, I expect theta % of them to be 1s and 1 minus theta % of them to be 0s. So in a way, sampling the distribution is just a way of creating fake data whose maximum if you use them to get a maximum likelihood estimate, you would expect, on average, the maximum likelihood estimate to give you back the parameters of the distribution you started with. Okay, so then how can we use this to generate a random sample of the entire joint distribution, FASHN? Right, we do the same thing we did when we used the factorization of the joint distribution again, right? So all we have to do is let's draw a random value for f, just like we talked about, using its conditional probability table, which of course has just one parameter, which is theta f. And then we'll draw a value for A the same way. Its conditional probability table just has a theta for A. But then we'll draw, given the values that we happen to randomly generate for F and A, we can now look up the term in sinus probability table that corresponds to these values that we just drew for F and A. And that'll tell us, suppose we draw a 1 and a 0. Now we just look at the conditional probability table for S, and it tells us what's the probability that S will be 1 given that assignment that we just drew for A and F. And that's just another theta, and so we use this trick again here. So we're using the sampled values for F and A to pick out the term in S's conditional probability table that we'll then use with this same algorithm to generate a value for S. And we can just march forward in the directed acyclic graph, which is the Bayes net, and at each step just pull out, given that we've already sampled FA and S, then we can find the right term here for generating a random value of H, and then for N. So it's very cool. We just iteratively apply this procedure, but now we do it n times for the n random variables in our graph. And that joint point that we generate, the values of those 5 variables, will be effectively drawn from the joint distribution on represented by that Bayes net. So why are we doing this? Because suppose I want to know P of n, again, P of n equals 1. Well, I could do it the way that I said, which apparently can be optimized further by ignoring one of the nodes. Or I could just generate 100 samples according to the joint distribution and then count which fraction of them happen to be n equals 1. See, so that's another just beautifully simple way of estimating probabilities. It's not always tractable to do that, but for small networks like this one, it certainly is. Okay, so all we do is, once we have this technique for generating random samples of data that follow the joint distribution of the Bayes net, then we can just treat those as though they're hallucinated data. They are drawn from that distribution. And given that data, we can then get anything we care about just by estimating it from this hallucinated data. Okay. All right, any comments, questions before we leave inference behind? Yes?
I'm not sure how this helps us because we don't know the distribution that we want to make this effective. So what do we get?
Well, if we're given a Bayes net, including the conditional probability tables, then we do know the joint distribution, right? In the sense that we have a way to calculate the joint assignment of any variable, of any variable, any joint assignment. Sorry, we have a way to calculate the probability of any joint assignment. So we do know it. And it's just that because inference over that Bayes net of particular terms like this can be arbitrarily difficult, one general technique is just generate a sample of data drawn from that joint distribution and then effectively use it to get a maximum likelihood estimate of this quantity. So if we generated 1,000 samples from that Bayes net, we would just ask, among those samples that happen to have H1 and N0, then what fraction of those also have F equals 1? And that would just be it. Yeah?
This sounds reasonable, but why do you say that's
Oh, weak because if I have a big Bayes net and small probabilities for some of these things, I might need to draw extremely large sample to get a reliable estimate. So, for example, if it turns out the probability of this is 0.00001, then I'm going to have a lot of samples even to see that occur one time. And so for that reason, I'll call it weak. Mm-hmm.
Suppose we're given a bunch of data. Do we get the Bayes net first, then calculate the Young distribution based on the net? Or we get the distribution from data, then we look at the data, we guess who might be depending on who. Because if we don't calculate the distribution, how do we know which variable is depending on what variable?
Yeah, very good. So you're saying, well, if we have a set of data, do we learn the Bayes net and then do these things, or do we learn the distribution in some other form and convert it to a Bayes net? Is that the gist of what you're asking? So we can do either. In fact, we'll talk the rest of the lecture about how we just learn the Bayes net directly from data. Here, I'm really not talking about learning Bayes nets. I'm just talking about if you have one, how can you use it to answer questions like this? Right? So for example, I might want to use that Bayes net right there to determine a patient walks in the door and gives me values for the 4 variables, but not for F. They don't tell me whether they have the flu. They just tell me, oh, I don't have any allergies, but I do have a headache and my nose is not running. Then I might want to calculate the probability of them having the flu given that they do have a headache and their nose is not running. And so once we have the Bayes net, the inference problem includes classifying patients according to whether they have the flu, right? And in general, the way the Bayes nets relate to our previous function approximation problem is that one of these variables here could easily be the thing we're trying to predict from the others. And so think of inference as not having to do with learning, but just having to do with once you've got a Bayes net somehow, then how are you going to use it to classify new examples, or more generally, answer any kind of question about the probability of a subset of those given others. Okay, good. So then, again, as I said before, there's a very intricate literature on doing inference in Bayes nets, mostly because in the end it is an NP-complete problem, and so there's a lot of work on particular structures of Bayes nets that allow more efficient inference, and these kind of Monte Carlo methods, including the sampling technique that I just mentioned, and other kinds of techniques. In this course, we're not going to dive into that because this is really more a course on learning than it is on probabilistic inference. But you should be aware that there's a lot there you can dig into if you're interested. Okay? But what I really want to do the rest of today is come back to the question of learning these things. Okay, so so far we've talked about how Bayes nets represent probability distributions. We just here in the inference part talked about, well, if somebody gave us a Bayes net, either because they learned it or they made it up or something, how would we use it to infer answers to probabilistic questions? And now the question of how we learn it, well, if you think about it, in fact, there are 4 kinds of learning problems for Bayes nets. We might be given the graph structure, or we might not. And we might be able to observe all the variables that are mentioned in the Bayes net inside our training data. We might have observed values for all those, or we might not. That second case we haven't really talked about in the course, but we'll talk about it today. Okay. So the easy case, so having the graph or not, and being able to observe all the variables or only a subset of them, gives us a little four quadrant design set of learning tasks. The easiest one, of course, is when the graph structure is given to us and the data is fully observed. The hardest one is when the graph structure is not given and we can't even observe all the variables in the data. People do work on this problem, but it's a horrible problem. An interesting middle ground, which we'll talk about today, is where the graph is given to us, but we can't really observe all the data, in which case we can still learn something interesting. So let's look at this case very briefly. We actually talked about it last time in passing. And then we'll look at this case in a little bit more detail. Okay, so let's start with the easy case. Suppose that, we'll use our example here. Suppose that we're given a Bayes net graph. We're not told what the conditional probability tables are, but we are given a big table of data where every row in our table gives us the observed 5 values for a different patient. Right? So our training data is just giving us for every patient these 5 variable values. And we're also given the structure of the network. A doctor told us that this is the correct way to think about the joint distribution. So now the question is, how do we estimate those conditional probability tables? And the good news, as we mentioned last time, is this is a problem we've already talked about. You already know how to do this. We can just get the maximum likelihood estimate of each of the parameters in each of the conditional probability tables in the Bayes net. Right? So for example, here's one parameter here associated with S. This has a little conditional probability table associated with it, with a number of probabilities telling whether sinus will be 1 or 0 given the 4 possible flu allergy combinations, 0, 0, 1, 1, etc. And so let's just think about how we would estimate a particular parameter in this guy's conditional probability table, like the probability that S equals 1 given a joint assignment of I and J to its parents. And the good news is that's just like our old coin flipping maximum likelihood estimate problem. Right? All we have to do is look over our training data, and here if I use K to index into the kth training example, I just want to sum over all the training examples. And here I'm using a notation where delta is just an indicator function. It's 1 or 0. It's 1 if the argument is true, and it's 0 otherwise. So this is just a way of saying, let's count how many training examples have this property. And then let's also count in the numerator how many have that same property plus have S equals 1. And so this is just the proportion of cases for which F and A have I and J, the proportion of those cases in which S also has the value 1. Right, so it's just our standard maximum likelihood estimate. And so that's what we do. Actually, if we're in this easy corner number 1 of the 4 possible problems, where we have fully observed data and a given graph structure, then the only thing we have to do is just a whole bunch of maximum likelihood estimates. And of course, if we had only a little bit of data and we wanted to put some prior on that, then we could get map estimates instead of maximum likelihood estimates too, right? Just like we did for the coin flip. We could put a prior on the thetas. But it reduces to a problem we've already solved lectures ago. Okay. Now you might ask, really, don't those other variables influence us? Well, they do, but they're all observed. In fact, here's the way of convincing yourself that we can get away with this. Let's do another maximum likelihood derivation, just like we did before. In this case, I want to say, well, if I think of theta as a vector of parameters, theta here is the vector of all these little theta sub s given f and a, and theta sub h given s, and theta, all those. Just make them into a big vector I'll call theta. Then for maximum likelihood estimate, I want to estimate the vector of all the parameters for that Bayes net that maximizes the probability of my training data, right? And so if I just write out what is that, if I, again, K is my kth training example. Kth training example. Then the probability of the data is just the probability of these IID training examples, the probability of each observed set of values. This patient K had F, A, S, and H and N as their values. And of course, I can factor that, according to the Bayes net, into this product of terms. And if I want to maximize the log of that instead of it, of course, those are they maximize for the same value of theta, then that product of terms turns into the sum of their logs. And then if I want to solve for a particular theta in that vector, like the one for S given ij, for flu and allergy, I would just solve for where the derivative of this is 0. And the beautiful thing is when I take the derivative of this with respect to theta S given ij, none of these things, all these derivatives are 0. And the only one that's not is this one. Because that's the one that this parameter happens to be associated with. And so all those 0 out, and I'm left only with this one, which is here. And now, again, this reduces to our maximum likelihood derivation for the coin flip, which gives us this fraction of cases where S happens to also be 1, given the thing we're conditioning on. Okay, so it's this step really here that justifies why we can ignore all those other variables given that we have fully observed data. It's just because these other terms in the joint distribution really are uninfluenced by this theta, and so their derivatives all end up being 0. All right. So I included that just basically to have one more example of a maximum likelihood kind of derivation to see we haven't given up on our original strategy of solving arbitrary problems by deriving what the maximum likelihood estimate would be. The step from here to here is not straightforward, but it is identical to the one that we covered for coin flips. Okay, so that is actually the full story on training Bayes nets with known structure and a fully observed data. It's as easy as estimating coin flips, or for continuous variables, as easy as estimating continuous distributions. Okay, but now let's move to the more interesting problem, where we don't get to observe in our training data everything. So suppose, again, the doctor told us that she believes this is how the observable headache and nose features depend on flu and allergy. And by the way, sinus problem is not something we can directly observe. We can only observe whether you have a headache or whether you have a runny nose. And we can kind of infer maybe you have a sinus problem. But if we really collected data seriously for patients, the observable things would be the 4 things, but not whether you have a sinus problem. We might eventually do a bacteria test to see whether you have the flu and an allergy test to see if you have allergy. But sinus is kind of this latent, not directly observed variable. So in general, that makes it hard to calculate the maximum likelihood estimate for all the parameters of our Bayes net because we can't observe S in this case. And in general, we could have, let's say X is the set of all the observed variables, in this case, F, A, N, and H, and Z is the unobserved variables. In this case, it's only S. What we'd like to do is calculate, if we can get this, we can solve for the MLE, but now Z are these unobserved things, so we can't actually calculate them. So what do? The answer is we use a technique called expectation maximization, often called EM. You'll hear a lot about it in the rest of the course, and you'll see a lot of it if you read the literature in machine learning. It's a very important technique for handling the case where we don't have fully observed data. So what we do intuitively is very simple. We, instead of picking the theta that maximizes this, because we can't really, Z is not observed, we maximize the expected value of that, where the expected value is taken over the probability distribution on Z given X, according to parameters theta. So it's like, to be concrete, we can't observe sinus. We can only observe the other 4 variables. So we can't really get the full maximum likelihood estimate because we can't observe the S's in the training data. So instead, what we're going to do is we're going to maximize the expected value of that. In our case, in this case, given the probability of S, given the observed F, A, H, and N. This is our X. This is our Z. Right? X are the observed variables, Z are the unobserved ones. What this is telling us is if we can't observe it, we're still going to guess what it is and then take the expected value of this full data likelihood where we calculate the expected values using our estimate of the probability of the unobserved ones given the observed ones. And it turns out if we do that, if basically we iteratively estimate what values of the unobserved things would be, plug them in, and re-estimate our thetas, and then do that again iteratively, we converge onto that is the EM algorithm. And it converges to a guaranteed local optimum for this expected likelihood.
What does EM stand for again?
EM stands for expectation maximization. Too many syllables. Expectation meaning the expected value of this, and we're trying to maximize it by picking theta. Okay, so let's see a little bit more detail what that looks like. So as I mentioned, what we have to do first is we have to take our observed data and find a way of predicting of having the probability distribution on the unobserved data. So we need a way of estimating the probability of S taking on a particular value in each of the training examples. Right, so we might have 100 training examples of 100 patients. For each one, we observe those 4 variables, but we don't observe whether they have a sinus problem. And so for each of those 100 training examples separately, we want to estimate the probability that S has the value 1 or the value 0 and the value 0. We want both probabilities, given the observed 4 values for that particular training example patient. So that reduces to an inference problem. Right? We have a Bayes net. Suppose I give you a Bayes net, and you have to infer it from the others. Well, we know how to do that. I see. The way I wrote it here, we're trying to get the expected value of the joint probability of x and z and maximize that. So one way to do that, as we showed before, is it's just the sum of all the log of that is just the sum of all these logs. And so the expected value of this is, here's the log of the joint distribution. And we can observe all of these values except not S. And so what we're going to do is to get the expected value of that. Remember expected value? Expected value of x, remember, of any variable is just the sum over the values x can take on of the probability that x takes on that value times the value itself. Right? It's just the probabilistically weighted average value. So here we want the expected value of this quantity, which is this. And that's just, well, here's the log of the joint probability of the probability of the joint assignment FAS H and N. But now, since I can't observe SK, I have to take the expected value of this quantity by summing over the probability that SK takes on the value 0 or 1, just like here. So here I is this whole quantity whose expected value we want to get. And the probability that we're using to weight the different terms here is just the probability of SK being 0 or 1. And so we'll get the probability that it's 1, and we'll multiply it times this joint, where S then is 1. And we'll get the probability where it's 0, and add that in. Okay. Now, you already, I think, know how to get this. I don't have a slide on it, but somebody tell me, how would I calculate this from the current Bayes net? How many here's the simpler question. How many rows in the joint distribution table would I need to look at in order to answer this question? How many joint assignments will I need to calculate? Two. What are they? Really? This is just a simple inference question in Bayes nets. Forget about Bayes nets. Suppose I gave you a joint probability table, and I said, get me the probability that one of the variables has the value 1 given the value of all the others. How would you do that? Okay, you guys are blanking out on me, or this is so trivial you're not telling me. It's just the probability that Sk equals 0 and f takes on little f and a takes on little a and little h and little n over the probability of that same thing plus the probability that s equals 1. Definition of conditional probability, right? It's just the probability of s being 0 over the probability of all the other things being true, marginalizing out s. You knew that before we started talking about EM. Okay, so this is an easy thing to compute from our Bayes net. It's just that we don't have a Bayes net yet. We're trying to learn it. And so that's what EM is doing. EM iteratively re-estimates the thetas, then uses those re-estimated thetas to calculate this term, the probability distribution for each of the unobserved variables. And then we can maximize this. It's called EM because E stands for expectation, meaning calculate all these expected values of the unobserved variables or their probability distribution. And then the M step is to actually solve for the theta that maximizes this quantity. Okay, so when you put this all together, you get a fortunately very intuitive algorithm, which looks like this. Suppose in general, we have a Bayes net with some observed set of variables x and some unobserved set of variables z. Then here's the algorithm. Just make up some thetas to begin with, and then iterate this process. On the E step, we estimate the values of the unobserved variables using our current theta, even though initially we just made it up. And of course, using the observed values. So we go through each patient in our training set, and we estimate the probability that they do or don't have s equals 1, whether it's s equals 1 or s equals 0, using our current theta plus the other observed features of that patient. Then on the M step, we use the observed values plus those estimates that we got for the unobserved data to derive a better theta. And in fact, it's the theta that we solve for the theta that maximizes this quantity. We just iterate this. So intuitively, what it's doing is we make up a bunch of random thetas to begin with, but then as we use those to estimate the probability of distribution on our unobserved variables, we can then use those together with the observed ones to get a better estimate of what theta is. And now we use that better estimate to redo this, to estimate better values for sinus. And then we use those even better values for sinus to get a better estimate of theta, and we iterate. And when I say better, precisely what I mean is that on every iteration, we're increasing the expected value of the joint likelihood, the likelihood of all the variables, both the observed ones and the unobserved ones. But since we can't really observe those, it's really the expected value of this joint data likelihood using this conditional probability as prescribed by the Bayes net. So on every iteration, this quantity gets higher and higher, meaning that the values that we're estimating for the unobserved variables and the thetas that we're estimating make the whole joint probability more likely. Okay. So that's the informal definition. To be a little bit more precise, here's what it looks like mathematically. We wanted the easy way to state it, and this is a very general procedure. It holds for any probability distribution you make up over any set of random variables. You can use EM. And here's the general description of the algorithm. We'll make up this quantity that I'll call Q. Q is just a function that's going to get me the next estimate of theta given the current estimate. And so we define that function as it's a function of theta prime given a theta. So given my current estimate, theta, I take the expected value of this, and then Q of theta prime is the argmax of this whole thing. I'm sorry. Q of theta prime is just the function that gives me this quantity as a function of theta prime, where my theta is held fixed. So you think of Q as a function of theta prime, given the parameter theta. And so then here's the general statement of the EM algorithm. We use the observed data x and the current estimate theta to get the probability distribution over the unobserved variables. And then we solve for the theta prime that maximizes that quantity. And in general, this very general algorithm is guaranteed to increase on each step the expected value of the joint likelihood, including those unobserved variables, where the expectation, again, is taken over this distribution, which itself depends on theta. And so if we iterate that until it converges, and often this will converge in like under 20 steps for reasonable size problems, then we end up with an estimate both of theta and of the values of those unobserved variables. So we're kind of simultaneously filling in the missing values in the training data and estimating what theta would be. Okay, it's going to, let's, I see, so we already talked about this. So if we ground this out in our particular example, if you were ever asked to implement an EM algorithm, say for this network, what you'd have to do to implement it is you'd have to figure out how to do the E step for your particular network, and then how to solve for the theta that maximizes the Q function. So in this case, if S is our unobserved variable, then it's pretty straightforward. On the E step, what we're going to do is what we already talked about. That is, we want to get the probability distribution over our unobserved variables, which is just S. That's also that's also the expected value of S itself. It's the probability that S will be 1 times 1 plus the probability that S will be 0 times 0. So it's just the probability that S will be 1. So it's the expected value of S taken over this distribution. And that's just as we said before. It's the ratio of those joint assignments, right? So that's the E step. That's all you do. It's actually very simple. So each E step, what we're going to do is for every one of those K training examples, for each training example separately, we're going to estimate the value of S for that particular patient. So now we have a table of training data with missing values, but for each of those missing values, we have probabilities that S equals 1 and S equals 0. And now on the M step, we have to estimate, we have to update theta to be the one that maximizes the expected joint probability of the observed and unobserved data. And if you work it out, which I haven't here, it turns out the way that you maximize that, the way you'd work this out is you'd write down the expression for the expected joint distribution. You'd take its derivative with respect to theta. You'd set that to 0, the same way that we do our MLEs. If you work that out, it turns out the quantity that you get is this. You're looking now for example, if you're trying to tell if S equals 1 conditioned on flu being I, value I, and allergy being value J, then you end up again with a ratio over all examples where flu and allergy take on those values. How many also have S equals 1? But now you don't know whether S equals 1, you just know the probability that S equals 1. Right? So this is really just the probability that S equals 1 given those observed things. So what you're doing is it's like every time you inferred that for a particular training example, let's say the probability of S equals 1 is 0.7, and the probability that it's 0 is therefore 1 minus 0.7, 0.3. Now what you're doing effectively is you're treating every example as a fractional positive example and a fractional negative example, according to that probability that you just got. So that's what the actual solution to maximizing this expected likelihood boils down to, this very intuitive thing. And if you go back and think about our normal way of doing maximum likelihood estimates, if we have fully observed data, if it's fully observed, then it was just this. We're just going to take the fraction of cases where F and A take on their values. What fraction of those also have SK equals 1? And so the only difference between this and this is that because we don't know whether SK is really 1, we can only use the probability that it's 1. So it's very intuitive, reasonable algorithm. The beauty of it is that you can prove that this converges to estimates of S and theta that maximize the expected joint likelihood over all 5 variables. When I say maximize, I should say locally maximize, because in general, these can be problems with multiple local maxima. Okay, I think maybe the most useful thing to do is to look at an example that ties this all together. So let me just state then that here's a very general technique. For example, in the case where we have Boolean variables in any Bayes net, then here's a general implementation of EM. Basically, for any Bayes network that has Boolean variables like that, we can take the observed ones and the unobserved ones, apply EM to estimate the parameters theta and the values that we're missing by iteratively doing this step, where on the E step, basically we just do standard Bayes net inference to estimate the expected values of each of those unobserved variables. And then on the M step, we get MLE estimates that are just like they used to be, except that where we used to count how many times a particular value takes on a particular variable takes on a particular value. If that variable is unobserved, we just replace instead of counting it as a 1 or a 0, we count it as the probability that it's a 1 or the probability that it's a 0. It just becomes a fractional count. So this just falls out as the general method for any Bayes net that has Boolean variables. It just turns into this simple strategy. And when we're counting the number of times it's y equals 0, we just take the probability that y equals 0, which is 1 minus the probability that it's 1. It's a very general technique. Okay, so let's look at one example which you'll hopefully love. Naive Bayes. So we can tie this all back. You told me a couple lectures ago that this is actually the Bayes net representation for naive Bayes. All of the x sub i's are conditionally independent given their immediate parent y. Right? And if I want to train naive Bayes, up till now we talked about how we could train it if we have this set of observed data. Right? Then we would just get maximum likelihood estimates for p of y and also for each of the p sub x sub i's given y. And we could use the first 3 rows in our training data to get those estimates. But now with EM, we actually can use these other rows where we don't really know the value of y, the variable we're trying to predict. So what does that boil down to? Well, remember what EM is. EM is an algorithm that's going to simultaneously learn the thetas, the parameters of the probability distribution we're trying to learn, and simultaneously estimate the probabilities that each of these missing entries is a 1 or a 0. So if we just apply this straightforwardly, remember I said in the previous slide that we could use this for any Bayes net that has Boolean variables. It just breaks down into this simple algorithm. So if our naive Bayes example is built out of Boolean variables, it's that simple. All we have to do is, on the E step, calculate for each training example the expected value of each of those unobserved entries, each of those unobserved y's. And that breaks down into what should be by now a very familiar expression for how you take a naive Bayes classifier and classify a new example. Right? The probability that y equals 1 given all the x sub i's is just this. This is what we always said when we talked about naive Bayes. So on the E step, what we do is we take our current set of thetas and effectively we classify these 2 examples and we predict what the y would be. In fact, we predict the probability that y will be 1 here and separately here, and we predict the probability that y will be 0, which is just 1 minus that. And then we use those fractional counts. Suppose here we predict the probability that y equals 1 is 0.8. Then this becomes 0.8, an example for y equals 1, and 0.2, an example for y equals 0. Right? That's all this algorithm was saying. On the M step, we just do our standard MLE style estimates, but we replace the count of the observed thing being 1 by just the expectation that its value is 1. And the count for 0 by the expectation that the value is 0. Okay, so if we do this, that's the E step. The M step also turns out to be just this analogous thing to our old naive Bayes training method. Remember the old naive Bayes method, if we got maximum likelihood estimates for x sub I given y, we just count the number of times y has that value and x has its value over all the examples. Now we're going to take because we can't really observe y, we're going to take, whoops. Yeah, now we're going to take the probability that y has that value, given all the observed stuff, times the counts, the observed cases. Remember, this is our indicator 0, 1 function. So in other words, the numerator is all the cases where xi has the right value, and the expectation that y has value m. And then the denominator, again, is just the total mass associated with the probability of y having m. So this generalizes in a beautiful way our old naive Bayes, but the result is that now we can, using EM, we get to now use these unlabeled examples as additional training information to support learning our naive Bayes classifier. And as a side effect of using this data, we also end up getting predictions for the y values that we're missing. So if you try this, it turns out my friend Kamal Nigam here, former CMU student, who is now a co-director of the Google lab here in Pittsburgh, he did some experimenting with this, applying naive Bayes to the 20 news groups data, which is a collection of text, which I think you might be familiar with, where each document is from some news group. He used some other data sets too. But when he applied this, what he did was he just trained a naive Bayes classifier given a bag of words style representation of a document, classify which of the 20 news groups it belongs to, that's the y. And he used some unlabeled data. That is, he didn't bother telling the program where some of those training news articles came from. So he had some labeled documents, which were labeled with a Y saying, oh, this is news group 5. And then he had other unlabeled, in this case, 10,000 other unlabeled news group articles. And then he just applied this EM. And this curve shows the accuracy of the naive Bayes classifier as the number of labeled documents increase if we use standard naive Bayes using labeled data only. And this shows the accuracy he got with EM using these additional 10,000 unlabeled documents, which were processed at the same time. So you can see this is a kind of a typical curve you will see for EM, that if you don't have too much labeled data, then EM can be a very valuable way of making use of unlabeled data. But of course, if you have infinite labeled data, then you're going to learn the best naive Bayes classifier possible anyway, and the unlabeled data doesn't really help you. This is a very typical kind of result. Okay, so let's end there. The point here for EM, and we'll continue this on Thursday next week after the midterm. We'll pick up on this and go some more. But what you should get from this is the simple idea that just like maximum likelihood estimation was a reasonable thing to do if we had fully observed data, and simple training of Bayes nets from fully observed data is just maximum likelihood or MAP estimation. But EM allows us to also use incompletely observed data where some of the variable values are missing for some of the training examples. And there, all we have to do is a small change to say that instead of maximizing the likelihood of the observed only data, we say we want to maximize the expected likelihood of the full data. And this iterative procedure does that for us, at least to a local maximum. And as you can see, it can be practical in many cases. Okay, so come at noon, not at 11, come at noon during class time, next Monday, and we'll see you then.